Controlling the frequencies in tubes like these is the basis for several musical instruments, including the pipe organ and the woodwinds. Take a bottle or a tube or a cylinder and blow air over the top. It will resonate, and from this you can measure the wavelength of sound. And if you know the frequency, you can also measure the speed of sound. But why does blowing air over the top of a tube or a bottle cause it to vibrate? Try this. Take two pieces of paper and blow air between them. The pages flutter in the turbulence. And when you blow air over the top of a bottle or a tube, it also causes a turbulence. The open end of a tube is a place where the air is free to move in and out, an antinode. The bottom of the tube is a place where the air cannot move, a node, a location of node displacement. When it comes to waves, the wavelength is usually measured as the crest-to-crest distance, but this device only gives us a node-to-antinode distance. That's only 1/4 of the whole length of the wave. Therefore, 1/4 of the wavelength is equal to the length of the tube. Since this cylinder is 25 centimeters long, we know that the sound we are hearing has a wavelength of 100 centimeters, or 1 meter. Now, at room temperature, sound waves travel at 340 meters per second. And if the wavelength is really 1 meter, then the sound waves we are hearing have a frequency of 340 hertz. You can verify this on an oscilloscope. Or, if you have a 341.3 hertz F tuning fork, it will resonate when held vibrating over the tube. Hey, a perfect match. Well, pretty close. What if you don't own a 341 hertz tuning fork? Well, then you can add water to a tube to adjust its length. Here's another trick you can try to instead measure the speed of sound. Take a tube that's open at both ends and dip it in water. Then with another tuning fork of known frequency, try to find the resonance. One-fourth the wavelength seems to be about 29 centimeters. That makes the full wave about 116 centimeters. By V equals lambda F, velocity equals wavelength times frequency, the speed of sound is about 335 meters per second. Very close. What about double open tubes? Well, in this case, both ends are antinodes. But between any pair of antinodes is a node, and you can see that the wave that fits in here is longer than the tube itself. In fact, the wavelength is twice the tube length. These tubes will resonate too, and once again you can measure the wavelength and the speed of sound. Now here's one more piece of the puzzle. The higher harmonics. The lowest frequency that fits in the tube is called the fundamental vibration, and its wavelength is 4 times the length of the tube. The next highest vibration is the third harmonic, not the second harmonic, but 3 times because of asymmetry reasons. The next highest one is also an odd harmonic, the fifth harmonic, who does fit 1 wave in the tube and a little bit more, and its frequency is yet even higher. In the case of double open tubes, the symmetry allows for all integer multiples of the fundamental to resonate, not just the odd ones. However, the fundamental wavelength is now twice as long. Now it's time for a puzzle. If I cover the open end of this tube, how will that change the note that resonates? This little window is a place where the air can move freely in and out, an antinode. And so is the other open end of the tube, also an antinode. So the wavelength that fits in is twice the length of the tube. But if I cover the open end, I now have an antinode-node situation, and the wavelength that fits in there is now 4 times the length of the tube, which should sound lower in frequency. But will it sound lower? Yes. Cut.